Hello everyone, welcome back to the class. And before going to the further concepts of the chapter, that is electric charges and fields, let us have a small recap of what all we studied in the previous class so that we'll have a continuity in our concepts. So now, before going to the concepts of a field due to a uniformly charged finite plane sheet, let us speak again about what is Gauss law. So Gauss law tells you that just imagine there is an imaginary surface where that surface encloses certain amount of charges. So I gave you some example, that is, if this is the imaginary surface, within that whatever the charge might be, so that is what you're going to add up. So if I have got 5 coulomb plus 10 coulomb, okay, so total of 15 coulomb are there within it. So in case if I have got any other charge outside this imaginary surface, I am not going to mention or consider that charge. So I'll be considering the charges only within the surface. So this is something called as Gauss law. And going to the statement of what is Gauss law, these are all the equations, formulas, and how we are going to get the electric flux according to the Gauss law using Gaussian surface. And you have got electric flux formula, that is phi is equals to E dot ds. So electric field passing normally through a surface, it means. So what is electric field formula? It is 1 divided by 4 pi epsilon naught q divided by r square, and delta s. So ds and delta s are same, children. It is small surface. So if I write sigma over here, that is sigma, it tells you summation, summing up all the small deltas. Delta, yes, so delta s is small surface. So if I have got 1000 delta s, so adding all the 1000 delta s, that is small surfaces, you will get the summation of the entire object or a material, whatever you have chosen. So this is something called as phi. It is electric flux, where it tells you E into ds. So now you have taken out all the vector symbols over here, direction and vector symbols, and you have just written the equation. Next, going on to this one, you're summing up. As I told you, you're not considering only a small surface but many small surfaces to get entire electric flux of the surface whatever you are going to consider. So example, if this is the surface, I have taken a small distance, small surface. So in this way, if I take another small surface, another small surface, another, so I'm completing the entire surface of the sphere. So this is something called as summation of delta s. So summation, what do you do in the next equation? You're going to take this inside the equation, and you would get 1 divided by 4 pi epsilon naught q divided by r square sigma delta. Yes, you will get. So now as in your lower classes you might have studied about what would be the surface areas of different objects. In the same way, surface area of the sphere would be 4 pi r square. Just substitute this 4 pi r square in this formula, and finally what you would get, see like this, 4 pi r square, you have got substituted the surface area of the sphere. Now phi is equals to, what are the things you can cancel? It's 4 pi r square, 4 pi r square, and what is the remaining thing? It is q divided by epsilon naught. And what is the statement? Law, Gauss law is this one. So total electric flux through a closed surface, this is what I told you. So whatever the number of charges would be in a closed surface, that is your imaginary surface, Gaussian surface. So total electric flux through a closed surface is equal to 1 divided by epsilon naught. Epsilon naught means it is a constant absolute permittivity, so it depends upon which medium you have got. So if there is air medium within the sphere, you're going to consider that. If there is water medium, you're going to consider not epsilon naught but epsilon r you're going to consider. So epsilon naught is only for the free space, And continuing with the statement, total electric flux through a closed surface is equal to 1 divided by epsilon naught times charge enclosed in it. So charges inside that. So this is something called as Gauss law. And not only that we also studied about application of Gauss law. But as I told you, according to your continuous charge distribution, it has been you have got several formulas, like three formulas you have got. In that, it is according to one dimensional object, two dimensional, three dimensional. So if I consider this application of Gauss law, you're going to apply Gauss law for every different dimension. So firstly, I have taken the linear charge distribution. Now, speaking about linear charge distribution, you have total of three formulas you should use. So, in that, before going to explain what is the formula, you have got a rod which has got it is infinite, and it has got a positively charged rod, it is okay, and it is enclosed by a Gaussian surface. Okay, so you can see the marking over here, it is Gaussian surface. Now if I consider this long wire or long rod, it produces some electric field as it is positively charged, and the cylinder's length would be, I consider it to be as L. So now taking the electric flux formula of what, phi is equals to E into surface area of curved surface. Now if I consider this would be this cylinder, the electric flux, the electric field which the tiny rod, the linear long rod produces, would be always perpendicular to the surface. Okay, so it is perpendicular to the surface. As from the law of electric flux, if I consider, taking a small direction vector, so I can say that the electric field is produced in this way, and if this is the little bit surface where the electric flux passes through it, electric field passes through it, and this surface has got a direction vector along it, and the direction vector and the electric field are on to the same side, and it is parallel to each other, then the angle would be 0. Okay, so before that, if I consider the surface area of this cylinder where the electric field passing through this cylindrical surface, I would consider the surface area to be as 2 pi rl. Why 2 pi rl? Though it is a cylinder, the rectangular part of the cylinder I am going to consider, but not the bottom or the top of the cylinder. Why is it? Because this rod is infinitely long, and so I never consider the top or the bottom, because this also would be infinite, and only the thing which I'll be considering is the rectangular thing, the surface area. Okay, so now this is something called as electric flux, where you have substituted the surface area of the curved surface. Okay, so it is 2 pi rl you're getting. Now going to the further, by charged enclosed in the Gaussian surface, as this is your linear charge distribution, because you have got one dimensional rod, no, so you have got a formula, that is, actual formula is lambda is equals to q divided by L. So this L has gone here because I wanted q, value of q, to be substituted, and using Gauss law. What is it? Why do I use Gauss law? Because your thin rod is being enclosed with a Gaussian surface, and obviously I require formula of Gauss law. So phi is equals to q divided by epsilon naught. And if I consider this formula, why do I keep q as onto my left hand side? Because I need to substitute the value of q in this formula. So I have already substituted and have given the value here. So phi is equals to lambda L divided by epsilon naught. So which I have equalized with what? As with this formula, this value is also phi, so this formula is equalized with this one. this formula. Okay, so both have been equalized because both are electric flux formulas. And what is the aim of this derivation? It is to find the electric field. So I keep E as it is and take all the things onto my right hand side of the denominator, where I cancel L. And finally, what would I get? E is equals to 1 divided by 2 pi epsilon naught lambda divided by R. Next, going to another application of Gauss law, but it is not one dimensional, but it is a two-dimensional finite plane sheet. What is it? Finite plane sheet. So here, before going to all this considerations, I would just like to give a pictorial representation where you have got a finite plane sheet. Okay, so now through this, if I consider this finite plane sheet, this is positively charged. So this produces electric field on to its both the sides. So if I consider a small rod, it is being fixed through this finite plane sheet. So through this I have center rod. So this rod has got two surfaces, that is small surface ds and ds. Now if I consider charges of this plate within this rod. So there are some charges within this rod also, if I consider, because this rod has gone through the finite plane sheet. So obviously at this region you would find some positive charge, and these positive charge would radiate some electric fields on both the sides. So by using the Gauss law, you have got a formula phi is equals to q divided by epsilon naught. So now if I consider the value of phi here, same thing as you did a derivation in this one dimensional, that is your infinite long straight wire, charged wire. The same way you're going to substitute and derive an expression for electric field. So now if I consider the value of phi according to electric flux, it tells you it is twice of area of electric field. So now what is it? What exactly is the formula? Going back to the previous derivation, it tells you E into surface area of the curved surface. Okay, so now coming back, just remember it is E into surface area. So now if I come back to this slide, phi tells you twice 2 E, that is E means it is your electric field, and A is your area. So why 2 they have written? Obviously you have got electric field into surface, no? So you have got two surfaces over here, and that is why 2A it's been given into electric field. So this is the formula according to electric flux. So that is equal to sigma A. What is this sigma A? So your plate, whatever plate you have got, it is what? It is a two-dimensional. According to your continuous charge distribution, it is being represented by sigma A. So your Q is equals to sigma A. So hope I have made it clear to you. So in the place of Q, you are just going to substitute what value? Sigma into A, where A tells you it is a surface area divided by epsilon naught. Here A and A have been cancelled. So E would be equal to sigma divided by 2 epsilon naught, where n gives you a direction vector where the electric fields have been radiated. This is all about your application of Gauss law according to what? Finite plane sheet. So next, going to another concept, here you'll be studying or you will understand what exactly is a Gauss law, and if I consider a Gaussian surface, what would be the electric field? of that Gaussian surface or the charge within it. So you have got two cases where you have got case 1 and case 2. So before that, let us read this. Electric field at a point due to a uniformly charged thin spherical shell. So okay, so they are telling you electric field at a point due to a uniformly charged. So if I consider one sphere, it is uniformly charged, and this uniformly charged spherical shell tells you about what would be the electric field this shell is radiating. So with respect to what? With respect to your Gauss law, where you have got your Gaussian surface. So now if I consider case 1, it tells you that field at a point outside the sphere. So now if I consider this is the sphere, on the sphere you have got some charges. On this sphere you have got some charges where your Gaussian surface is surrounded through it. So you have got one surface, Gaussian surface. Within that you should find out what would be the electric field. So now if I consider the formula, phi is equals to E cos theta into delta S. So what is it? E cos theta into delta S. So why cos theta? It is telling you which component you're going to use it. Now if I consider this would be a small surface and the electric field is radiated. So the direction vector and the electric field are together, it is parallel to one another, and that is why you can see that the angle between them, as it is parallel, the angle is 0 and cos 0 becomes 1. This is what we have studied in our concepts of electric flux. So you can go back to the video and check with it. Next, going to an further of the derivation, if I consider sigma, so what is it? Phi is equals to E sigma delta S. So small surfaces, you're going to add all the small surfaces, you're going to get the entire surface. So sigma S tells you about the surface area of the sphere. So if I consider this would be the sphere, the surface area of the sphere is 4 pi r square. So you're going to substitute this value over here, and what do you get? Phi is equals to E into 4 pi r square. Now according to the Gauss theorem, so Gauss law, if I consider this is the Gaussian surface, so what is the formula you have got? So it is phi is equals to 1 divided by epsilon naught. So phi is equals to 1 divided by q by epsilon naught. So total charge enclosed you have got, so you're just going to multiply with q. So you have got phi is equals to 1 divided by epsilon naught q. So if I consider the electric field now, what would be the value? So what is it? You have got the value of q, you substitute this value here. Okay, q divided by epsilon naught. So q divided by epsilon naught you have got, q divided by epsilon naught you have got. Now what you're going to do in this, after you substitute here, take 4 pi r square to your left hand side of the denominator, that is just do it ulta. Hope I am making you clear with this. So finally what you would get, q divided by 4 pi epsilon naught r square you're getting. This is your total electric field due to what? Of a spherical shell which is enclosed by a Gaussian surface. So what was the main thing here? On the surface the charge was positive, some charge was there. Now there is case 2. Okay, here you should be very much careful. So E at a point inside the shell. So they are telling you, if I consider this is the spherical shell, inside that find the electric field, they are telling you. So now you should understand that this is your spherical shell. So this dotted line is your Gaussian surface. So this is your spherical shell, I told you. So this shell, on the top of it you have got some charges but not within it. So what do you mean the charge is 0 inside this shell? So it means that a positive and a negative charge have become neutral. and that is why their charge is neutral, charge is zero. You understanding? So if I consider the shell, within this shell the charge would be zero. On top of this, in the next chapter you would find that saying that the objects have got charges on their surfaces. Okay, these are the properties you would get in your next chapter. Okay, so what do they say? If I consider this is the sphere, on top of this you have got some charge, but within this sphere there is no charge. So now if I consider this a Gaussian surface, inside this Gaussian surface the charge is zero because it is neutral, no, that is why the charge is zero. So what do you mean by Gaussian surface or Gauss law? The total charge enclosed within the enclosed surface. So if I consider this is the sphere has got charges on the outermost uh, surface but not inside. So if I have got Gaussian surface inside the sphere and there is no charge, and that is why you can see that phi is equals to, what is the formula for the Gauss law you have got? It is total charge enclosed, so q divided by epsilon naught. Okay, so what is the number of charges? So within this Gaussian surface it is zero, it is zero, and the electric flux is entirely zero, and you do not have any sorts of electric field when I consider electric field at a point inside the shell. So inside the shell there is no electric flux, no electric field. So this is something called as the Gauss law, where inside or the outside of the shell you have got two cases. So in our today's class we studied about the applications according to one dimension, two dimensional objects. So the one dimensional is something that it's a charged a long infinite rod, and it was, if I consider this two dimensional, it was what, it was a finite plane sheet. Through that, what would be the electric field we understood, and also we derived it. And with two cases we understood how would a Gauss theorem work on it. So this is all about your first chapter, and till here your entire chapter and all the topics of this chapter is being covered. So in our next class we'll go with the numerical problems, and later on we'll jump on to the second chapter. And second chapter is also very very easy, only if you understand and follow what do I say. Okay, so if you have liked the video, if you have understood the concept only, then please do like, subscribe my channel. Thank you.